Hello year 12s. I hope you're having a good long weekend. And I know you're probably thinking, why is Miss working on a weekend? Because Monday is upload day, so Monday public holiday or not, Monday we work. Alright, so today we are going to complete section 1.3 in your textbooks, which is basically all of the gravitational and rotational stuff. So we are starting from page 91, which, well, we left off after the questions. So we're looking at on a flat curve, the friction force between the tires and the road causes centripetal acceleration. To improve safety, summarize the bank at an angle above the horizontal. Draw a diagram to show force vectors and their components for vehicle traveling around a flat curve and around a bank curve. Explain how bank curve reduces the reliance on friction to provide centripetal acceleration. Alright, so important things to note from this section of the course. 1, how to draw the diagram, and 2, the different formulas you need to use. So I'm just going to show you the book without getting hit in the face by said book. Okay. So we have the top view of our diagram and then the back view. So looking at it from the back. So looking at it from the top, we can see that this car is going around a curve. As it goes around a curve, there's a force, the velocity driving it forward and the force pulling it to the center of the curve. Right? And then in this diagram here, we have, so if we're looking at the same thing, but from the back, the force is pulling the car inwards towards the inside of the curve, as well as the normal force pushing it down, and the normal force pushing it upwards, and normal force pushing up, weight pushing it down because of gravity. Okay, so that's how we draw the two diagrams. If something is going around a curve, acceleration going out, force going in from the top, from the back, force acceleration force of the centripetal acceleration is pulling it inwards. The normal the weight force is pulling it down from gravity, and the normal force is pushing it up from the top. Okay, so in order to find said force, or the static friction of the force, we do capital F. So for force, lowercase f for friction is equivalent to G. Okay, where capital F, lowercase s is friction force, is static coefficient, yes. Yeah, mass and G is gravity as always. So, define the force. We have F, lowercase f, is and subscript is equal to mu s m g. Friction force, the FF is equal to friction force. The mu s is equal to static coefficient. That is something that is given to you. That's a constant. We have the m, which is mass, and the g, which is gravity. That does not change. Okay. So we have that formula, and then we have three others that go along with it. F of f equals mv squared over r. Mu s m g is equivalent to mv squared over r. V is equivalent to the friction of ms g r. So I'm just reading the information that's on either side of this formula, explaining what it actually means. Right? So this formula here on this side, specifically this one here, shows the maximum speed is independent of the vehicle's mass and is dependent on the coefficient of static friction. The value of the coefficient is approximately 1.0 between rubber car tires, and the rubber is reduced between 0.4 and 0.1 when the road is wet or icy. Car's maximum speed around a circular arc is greatly reduced in wet weather. Okay, that's a given. I know you guys are probably all driving or have driven or getting your L's or your P's, whatever it is. You know, when the road is wet or icy, you slip around because there's no friction. Whereas the road is dry, you have a bit more friction, so you're a bit more sturdy. That's true when you're driving straight and also when you're driving around a bend. When you're driving around a bend, however, because your tires are not completely flat, they don't have the full flat against the road and you're turning, so some of the tire isn't completely flat on the road. It's also it's not facing the same direction. It's not parallel to the road. It's perpendicular at an angle. Because of that, you kind of slip a little bit when you're driving. Okay, so that's that. Then it looks at banked curves. So very similar diagram to the one we had before, where you have a car going around a curve. Friction force goes inwards. The velocity is pointing outwards. But on the back diagram, there is an angle, and so we have an extra force. We have the weight force pulling the car down, the normal force pushing it up. Then we have the angle pushing it out, and then the normal pulling it into the center of the circle. So, looks the exact same, but the one we're interested in is on here, bank curve. So we have force going down from gravity, we have the force coming up from opposite of gravity, then we have the angle force there, and then the force pulling it into the center of the circle. So if you get a test and it asks you to draw a banked curve at an angle, make sure you have those extra vectors in place. Okay. Which then leads us to how in the world do we calculate the speed going around something like this? For that, we have an equation. The final equation is v equals the square root of tan theta g. Okay, v velocity, tan theta is the angle, r is the radius, and g is gravity. Okay. That's a square root symbol. Yes, I know my handwriting is terrible. So v equals the square root of tan theta rg. V is velocity, tan theta is the angle, r is radius, and g is gravity. So we have that all together. So if you get a question that asks you to derive that from what we did in projectile motion and motion in 2 dimensions, and also from maths, tan theta is, what was it? Tan theta is sort of adjacent. In this case, it's the force of the normal height over the force of the normal vertical, not horizontal. Tan theta is the force of the normal horizontal over the force of the normal vertical. Right, so therefore tan theta is equivalent to mv squared divided by, that's an r, isn't it? R over mg. So you should know from your forces, because the vertical force, you have the mass of the car plus the speed divided by the radius gives you that force going across, and then the height, we have the mass and gravity going down. So if you look at the diagram on page 92 next to the formula block, we can see where they are getting all this information from. So yeah, specifically down here, there is the normal force going down, the angle force going across, and then the force of the horse. So horizontal force that way, vertical force that way, and our normal on the angle there. So we're doing this part here with the derivative. Now, not coming out today. the derivative, they're deriving it. Anyway, so tan theta, the bottom angle there is equivalent to horizontal force over the vertical force. So the horizontal force is mv squared over r, and the vertical force is mass times gravity. Mass cancels out, so tan theta is equivalent to v squared over rg. Then to get velocity by itself, v equals rg tan theta. Okay, so that's that entire process there. So how do we use this? So you're looking at example 1.41. We have a race car travels around a bank curve of a radius 250 meters with an angle of 9 degrees. Calculate the maximum speed a car can travel around the bank curve without reliance on friction. And then, so you're looking for the velocity. We don't know. Angle is 9 degrees and radius is 250 meters, and gravity is the constant of 9.8 meters per second negative squared. Okay, so we have all the information there. We plug that information into our formula that we just went through. Velocity is equal to the square root of 10 of 9 times by 250 times 9.8, which is equivalent to 20 meters per second negative 1. Okay, simple as. Alright, so question 83. It asks you to draw and label all the force vectors acting on the diagram above. So it has the diagram there, you just need to draw the forces. So make sure you have down, up, into the center, and then cause it's on an angle, the one pointing on an angle. Usually when you draw the vector, you draw the angle on a car. So you have, that's the car there. 1, 2, 3. Alright, that's your force. Gravity, force of the normal, force the normal horizontal, normal vertical, normal horizontal, and force of the normal as a resultant. Okay, so when you draw your diagrams, gravity, normal force as a vertical component, normal force as a horizontal component, and then the normal force coming out between the two. This only applies for angled diagrams. So you would draw all these vectors onto this diagram here. Okay? Alright. So we will leave the questions, skipping ahead onto page 97. So looking at Newton's law of universal gravitation. It's one of my favorite formulas. So force is equivalent to G m1 m2 over r squared. Right? So F is a gravitational force. G is constant of universal gravitation. M1 is mass of lighter object. M2 is mass of heavier object. R is distance between centers. Okay, gravitational force units is newtons. Constant of universal gravitation is newtons per meters per mass squared in kilograms. Negative squared. I don't know, maybe it is meters. Nm squared kg. Yeah. Turns out it is meters. Alright. Mass of lighter object is in kilos, mass of heavy object is in kilos, and distance between centers is in meters. Okay? All this information is on page 97. Okay? So, the universal constant is equivalent to 6.67 times 10 to the negative 11 nm negative 2 kg negative 2. Okay? That is what the universal constant is. I know that looks like a 6. That is a G, not a 6. Okay? Alright, so how do we use it? Great question. So, next page. Example 1.42. We have calculated the gravitational force between two 95 kilo boxes separated by 0.7 meters. Okay, so it wants us to find the force. Force unknown. G, we know, 6.67 times 10 to the negative 11. I really need to work on writing my G's. Mass 1 is 95 kilos. Mass 2 is also 95 kilos. Why? Because they're in the same weight class, therefore they have to be the same weight. And our distance, our radius, is 0.7 meters. Alright, so we have all our information written out. Then we write out our equation, F equals G m1 m2 over r squared, and we plug in our information into the equation 6.67 times 10 to the negative 11 times by 95 times 95 and 0.7 squared. That'll thing. Make sure you put brackets in when they are needed, and you should get the answer of 1.2 times 10 to the negative 6 newtons is the force between these two boxes. Okay? They're fairly easy questions. If you're given the information, you just chuck it into the equation and you're done. That's why I like it, because it's easy. Alright, next we have acceleration due to gravity. So, on page 99, it starts off with figure 1.34 shows a mass positioned at the surface of Earth. Surface of Earth. The gravitational force between the centers of the mass and the Earth can be calculated using Newton's law of universal gravitation and the second law of motion. Two formulae are mathematically equivalent and are used to derive a formula to calculate the value of acceleration due to gravity on a planet, moon, or star. Okay? So, Newton's second law, we know that F equals ma. Okay, but specifically with planets is F equals mg. And now we have this other gravitational formula. We make the two equivalent. So cancelling out the F's, so mg is equivalent to capital G m1 m2 over r squared. Alright, we cancel out m on the one side and 1m on the other side, so G is equivalent to G m2 over r squared. Okay, look at that. Look at that. Isn't that nice and easy? Yes, it is. It's great. Okay, so you may ask, how do we use this formula? Great question. Let's look at example 1.46. So Earth has a mass of 5.97 times 10 to the 24 kilos and a radius of 6.37 times 10 to the 6 meters. Calculate the acceleration due to gravity at Earth's surface. So, lowercase g is gravity. We don't know what that is. We have our mass, which is 5.97 times 10 to the 24, and we have our radius, which is 6.37 times 10 to the 6 meters, and this is in kilos. Great, so we have our information. So, gravity is equivalent to the g constant, 6.67 times 10 to the negative 11 times by 5.97 times 10 to the 24 divided by 6.37 7 times 10 to the 6, put that in brackets and squared. So you're plugging that bottom on this line here into your calculator with the brackets included, and you should get the answer 9.81 meters per second negative squared. Right? -2. Always -2 for gravities, because it is an acceleration, therefore -2. Alright, so the derived formula shows that magnitude of acceleration due to gravity decreases as you get further from the planet, moon, or star. Okay? Bigger radius, less gravity effect. As in, the further away you are from the planet, the less the gravity affects you. Okay? Acceleration, blah, 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 blah. So, there is a nice diagram there explaining the acceleration due to gravity distances from the Earth's surface. So, the further away you get, the slower the acceleration is. Okay? Then there's a bunch of questions. I'll leave you to them, and we skip ahead to page 104. Alright, page 104. Objects with mass produce a gravitational field in the space that surrounds them. Like Earth does when it pulls us down. If you're in space, you get pulled down to Earth. Okay, same with the sun. We are slowly getting closer to the sun every year. So an object with mass experiences a gravitational force when it is within the gravitational field of another mass. Gravitational field strength, G, which is what we use for gravity, is defined as the net force per unit mass at a particular point in this field. This definition is expressed quantitatively as G with an arrow on its head, because it is a vector, is equivalent to force over mass. Hence, it is equal to acceleration due to gravity. The magnitude of the acceleration due to gravity at the surface of the Earth is 9.8 meters per second squared. Alright? That's pretty self-explanatory. Think about it. Things with large mass have a gravitational field. Things are drawn to it, the bigger it is. The bigger the object is, the bigger the gravitational field is, the more things that get drawn to it. There's a lovely diagram on page 104 that explains this. It shows what it looks like. So you have a planet, they have vectors going into the planet, and then you have two masses. So gravitational field exerts a gravitational force on any mass positioned inside the field. The gravitational force increases as the mass approaches the center of a planet. We know this. That's why we have different height satellites. That's why we are stuck to Earth and all the rest of it. Alright, so going on to page 105, gravitational field strength. So magnitude of a gravitational field is at a given point is called the gravitational field strength. Gravitational field strength is defined as the net gravitational force per unit mass at a given point in the field, and it's calculated using the formula below, which is G with a line on top of it. With a line with an arrow on top of it to show that we are talking about gravity, the gravitational field, specifically not just gravity itself, the gravitational field over force divided by mass. Okay, so as you know, gravitational field units are N, kg, -1. Excuse me. Force is units is newtons. Excuse me, what is wrong with me? And the mass units is kilos. Okay. Okay. So gravitational field strength is mathematically equal to the acceleration due to gravity as shown in the derivative below. And sorry, not the derivative, derivation below. Alright, so we have field strength is equivalent to acceleration due to gravity. So we make those two formulas equal. Gravity, lowercase g with an arrow over it, is equivalent to F over m. Okay? Which goes out to, remember we used the gravity formula earlier, capital G times m1, m2 divided by r squared over m. We're swapping out the force for that gravitational theorem. Okay, is equal to the r drops down to the bottom, so we have G m1 m2 divided by mr squared. Here is two m's cancel out, so we have G m2 over r squared. Okay, that's it. That whole lovely thing. Okay? Gravity is force over mass. We swap out the force for the gravitational constant thing that we went through earlier. So gravity is equal to gravitational force, gravitational constant times mass 1, mass 2 divided by r squared over mass. The mass 1 and the mass cancel out. So then we're left with gravity is equal to the gravitational constant times by mass over radius squared. Ta-da! Right, so how do we use that? Good question. Let's go to example 1.47. Alright, so Earth's gravitational field exerts a net force of 49 newtons on a 5 kilo book positioned at the surface. This book is not 5 kilos. I take that back, maybe it is 5 kilos. Alright, so calculate the gravitational field strength on the Earth's surface. I said that because in this textbook, the picture I have is of the physics book. And I did not think it was 5 kilos, but it might actually be 5 kilos. Anyway, so we use our formula. Gravity is equivalent to force over mass. Gravity is equivalent to 49 newtons divided by 5 kilos, which equals to 9.8 meters per second negative. Oh, hold on. 9.8 newtons per kilo negative 1. Okay, so when we're looking at gravitational fields, make sure you use the right units, which is newtons per kilo is negative 1. Do not automatically put meters per second negative squared. Okay, we're not talking about acceleration at the moment or gravity at the moment. We're talking about a gravitational field. A gravitational field is G with the arrow on top. The units are newtons per kilo to the negative 1. Okay? Oh, and then there are questions. I'll leave you to the questions. Alright, next page 108. We get to look at satellites. Yay! Satellites are fun. Alright, so in the lovely blue box there, which is a summation of the chapter, we have many satellites orbit the Earth in circular orbits. As it's given. Explain why the centers of the circular orbits of Earth's satellites must coincide with the center of Earth. Explain that the speed and hence the period of a satellite moving in a circular orbit depends only on the radius of the orbit, not the mass of the central body. And derive the formula V equals the square root of gm over r for the speed of V satellite moving in a circular orbit of radius r about a spherically symmetrical mass m, given that its gravitational effects are the same as if all its masses are located at its center. Okay, so we have on page 108, figure 1.38. We have a height and we have the trajectory of 4 different satellites. Okay. Okay, so depending on the launch velocity of the projectile will depend on whether or not it is capable of actually keeping orbit with the planet. If it is not launched high fast enough, you get trajectory A, which is just a projectile motion thing. Down. Then you have trajectory B, where the surface curves away from the projectile, so it goes a little further, but still ends up hitting the planet. Then trajectory C, surface curves away from the projectile, goes around, makes it about 3/4 of the way before landing back on the planet. Whereas trajectory D, which has enough velocity to keep up with the speed of the Earth, it manages to form an orbit around the planet. Not necessarily Earth, but any planet. So projectile is in orbit when the curvature of the unit trajectory matches the curvature of the planet. The two things are important there. The angle of launch to match the curvature of the Earth, and the speed at which it's being launched at to make sure that it is in fact going fast enough to break out of Earth's orbit and still keep in speed with the orbit. Okay. Alright, so looking at the paragraph next to figure 1.39, which has projectiles in orbit. So in the absence of air resistance, an orbiting projectile is in free fall in which gravity is the only force affecting its motion. Gravity attracts the projectile towards the surface, but its tangential speed is so large that the curvature of the trajectory matches the planet's curvature. When this happens, the projectile falls under the influence of gravity, but never gets closer to the surface that is curving away beneath it. Okay, the direction of gravity force on the projectile changes as it moves around the planet, but is always directed towards the center of the planet. Okay, like we discussed last video, when you are spinning something on a string, it goes around, it has a normal force acting inwards and the velocity at a tangent going outwards. Tangent going outwards. Same thing when you have a satellite orbiting around a planet. Force is being drawn inwards, but the speed is going at a tangent outwards, which keeps it out and about, keeps it out and moving. Right? That's why when you send something into space and it orbits, it stays where it's orbiting. For the most part. If it starts to fall, you've not launched it correctly, and gravity instead acts on it and draws it in. Or it's hit something. Alright, next, satellites. A satellite is a small mass that orbits a large mass with the centripetal acceleration supplied by the gravitational force. Alright. Just me, figure 1.4 literally shows what I was just talking about. Okay? So, Newton's second law states the gravitational force exerted by the largest central mass on the satellite is equal to mv squared over r, where m is the mass of the satellite and v squared over r is the centripetal acceleration. Okay, this property of circular orbits is used to derive a formula to calculate the orbital speed of a satellite. So, you may be asked to derive this. First and foremost, you use the gravitational force formula for that. And that not the G equals M over A, the F equals G MM over R squared. Okay, so gravitational constant, mass 1, mass 2 over R is equivalent to mv squared over R. That's us get double button there. Okay, so this is what we're starting with. Gravitational constant, mass 1, mass 2 over R. Gravitational constant, mass 1, mass 2 over R squared is equivalent to mass velocity squared divided by radius. Alright, so we have one mass. Mass 1 cancels out with mass. R squared just becomes R, and we cross out the R on the other hand side. So we're left with G mass 2 over R is equivalent to V squared. Okay, we have this now. I'm going to get the velocity by itself. Okay, that means we square root both sides, so we end up with velocity is equal to the square root of G M over R. Ta-da! That's it. That's all it is, which is great. Alright, so what does this formula tell us? The exact speed a satellite needs to have in order to maintain a circular orbit at that set distance. Okay? Why is this important? Because if you want to have something, if you have a round planet and you're sending something into space, you want it to have the same nice round orbit. Okay, so you want the satellite to have the same circular orbit as the planet. If the speed varies, you will have an elliptical instead of a circular orbit. That's the difference between having a nice circle and an oval. Okay. Alright, so let's break the formula down. V is velocity, G is constant of universal gravity, universal gravity, M is mass of planet, that's not how you spell planet, and R is radius. Alright, when you use this formula, be mindful that the mass is not the mass of the satellite. It is the mass of the thing being orbited by the satellite. That is important. Right? So, once again, how do we use this formula? Great question. Example 1.48. So, Earth orbits the Sun, and it gives you the mass of the Sun and the distance that Earth is from the Sun. Then you can calculate the speed at which Earth orbits the Sun. So, speed is equivalent to a question mark. We don't know that. G is 6.67 times 10 to the negative 11. Our mass of the Sun is 1.99 times 10 to the 30 kilos. And our radius is, well, the distance between Earth and the Sun is 1.5 times 10 to the 11 meters. That is a big number. Right, so velocity, we stick it into our equation with the v equals the square root of gm over r. So velocity is equal to the square root of 6.67 times 10, brackets, times by 1.99 times 10 to the 30, close brackets, and then we divide the whole thing by 1.5 times 10 to the 11. So you can stick this whole thing into your calculator as is with brackets. Don't forget the brackets, and make sure your calculator is in degrees. Not that we're using angles at the moment, but double check. And your final velocity should be 2.97 times 10 to the 4 meters per second. That's very fast. Okay, well, that's it. Great. So, Kepler's laws. So, Kepler was a dude, as most people in physics were. Dudes that discovered things. What did Kepler discover? He discovered the laws of planetary motion to describe the motion of the planets, moons, and other satellites. Kepler's first law of planetary motion. All planets move in elliptical orbits with the sun as at one focus. His second law of motion, the radius vector drawn from the sun to a planet sweeps areas equal in equal time intervals. Nice. Describe Kepler's first two laws of planetary motion. Use these first two laws to describe and explain the motion of comets, planets, moons, and other satellites. Kepler's third law of planetary motion shows that a period of any satellite depends upon its radius of object. For Kepler's orbits, third law can be expressed as t squared equals 4 pi squared over mgm times by r cubed. We have to derive that and solve problems using the formula. Explain my satellite in geostationary orbit must have blah 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 blah. Okay, so we're basically now looking at satellites and Kepler. Kepler. Yeah. Kepler. Alright, so Kepler's first law on page 110. There is a great diagram showing that. So the sun is positioned at one focus, planets going around it, nothing lies at the other focus. Planet follows elliptical orbits with the sun at one focus of the ellipse. Focus is one of the two internal points that determine the shape of an ellipse. The distance from one focus to any point on the ellipse, then back to the second focus, is constant. An ellipse has an aphelion, the point in an orbit where the planet is farthest from the sun, and a perihelion, the point where the object is where a planet is closest to the sun. So you're gonna have to learn how to draw that diagram. And if I can do it, you can do it, because my drawing skills are terrible. So, first and foremost, we have a dot. We label this the sun. Okay? Then we draw an ellipse. An ellipse is an oval. Okay? Draw an oval, with the sun on one end, and then nothing at the other. It does not have to be a perfect oval. It can be a weird, ugly log like this, as long as it is ovular looking enough. It could be an egg. That's fine. Okay? Somewhere on this oval, there is a planet. Okay? Planet. Okay? And you can draw which way the planet is orbiting with little arrows on the orbit trail. Now, you need to know the side closest to the sun is the perihelion. Yeah. And the side furthest away from the sun is the aphlia. Why don't they just make a matching? Aphlia. Okay? Okay. That's basically the diagram you need to be able to draw. Sun, one focus, perihelion closest float to the sun, planets floating somewhere around, and this is the aphelion on the opposite end. Ta-da! Done. There you go. Kepler's first law. Drawn in a diagram. Nice. Alright, next. Kepler's second law states that as a planet moves in its orbit, it sweeps out an equal amount of area in an equal amount of time. In other words, a straight line joining the center of the planet and the sun, called the radius vector, sweeps out equal areas in equal time intervals. Shown in 1.43. Okay, so I'm not gonna be able to draw this for you. I'm going to have to describe this to you. So before we do that, first and second laws are used for describing the motion of planets. Okay, moons, comets, and other satellites. Basically any sort of satellite that we use. Elliptical nature of orbits results in a satellite having a greater speed at the perihelion and a slower speed at the aphelion. As V, as the formula we used earlier, V equals the square root of gm over r, where speed is inversely proportional to the orbital radius. Okay, so we know if it is closer to the thing it's orbiting, it's going to go faster around, and if it's further away, it's going to go slower. Okay. I always think of Futurama, and there's one episode where they have to slingshot around a bowl of garbage, and they're using this exact concept. So, we have this here. In a mostly circular orbit, we have this area here and this area here are equal, even though this area looks the point between A and B point. The space between this here and this here looks larger than this here and this here because it's closer to the sun. This part's closer, it's moving faster. So this here, even though it's covered a greater distance, is still 1 month compared to this here, which is also a month, even though it's moved less time. Okay, bit hard to see on a more circular orbit. On a highly elliptical orbit here, this halfway around is basically gone at a half and around is 5 months, and this tiny little sliver here is also 5 months. Okay? Because, once again, closer to the sun, moving a lot faster. Farther away from the sun, moving a lot slower. Okay? Alright, so, next. Kepler's third law is a formula, which is great. So, it relates period of a satellite to the radius of its orbit. Okay, so understanding the relationship between time and orbit distance. Kepler used astronomical data containing blah 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 blah. Maths to determine the relationship between the variables and discover the square root of the period of any planet is direct proportional to the cube of its orbital radius. Cool. Alright. So basically learning how to derive the period formula. So first thing we need is we did this circular motion. Alright. So if you remember from circular motion, pretty sure you guys did it last year, where force is given to 2 pi r over t. And then we also have the other force of, not force, speed. The speed of an object moving around in a circle is 2 pi r divided by t. And we also have the speed in a planet is the square root of gm over r. So we make those two things equivalent to each other. Square root of grass times mass. Gravity times mass divided by radius is equivalent to 2 pi r over t. This formula is from circular motion, which we did a while ago. Should have done it in year 11. Don't do it? Yes, we did do it. I'm not losing my brain. We did do it. V equals 2 pi r over t. Great. So we have done this before. Alright, so we have this that we did earlier, velocity of a planet, and this, which is velocity of anything moving in a circle. Okay, put the two together. Now, We want to get rid of that square root, so what do? Square the entire thing. Okay, that gives us Gm over r is equivalent to 2 squared times pi squared times r squared over t squared. Right? Now, we get rid of the r on the bottom by multiplying by r, which then makes it Gm equals 2 squared is 4, and pi squared says pi squared, and r squared times r is now r cubed over pi, sorry, not pi squared, over t squared. Okay, this is what we have now. Oops. Gm is equivalent to 4. That's a 4. Yes, I know it's not drawn properly. Equals 4 pi squared r cubed over t squared. We want to get t by itself, so we swap the t and the gm. So t squared is equivalent to 4 pi squared r cubed over gravitational constant times by mass. Okay? Ta-da! And that is where we get a formula. And I know that's not good. There we go. That's a bit of a better t. Okay, there we go. That's the whole thing. All done, all together. That is how you derive that. By using the velocity formula for gravitational constant and the velocity formula for anything moving in a circular object, you make them equal to each other and just knock it out. I'm sure you guys are all more than capable of doing it. You're all very smart kids. Alright, so we have that. Now let's use it. Alright, so example 1.49. International Space Station orbits the Earth at 5.97 times 10. Well, orbits the Earth and gives you the mass of the Earth with the radius. Calculate the orbital period of the International Space Station in minutes. Okay, remember when you do anything, it gives it to you in seconds, and you need to convert it into the unit as requested. So we have period equals unknown. We have our gravitational constant times 10 to the negative 11. We have our mass, which is 5.97 times 10 to the 24. And we have our radius, 6.78 times 10 to the 6. Alright, let's find our period. So t squared is equivalent to 4 pi squared r cubed over gm, which is, I want to get rid of the t squared, so the square root. Right, t, so let's plug that all in. I'm gonna get the whole thing here. So we have t by itself, because we square root the entire thing to get t by itself, is 4 times pi squared times by 6.78 times 10 to the 6, brackets, that's cubed, divided by 6.67 times 10 the negative 11 times by 5.97 times 10 to the 24. But it should look something like that. I'm going to stick it into calculator, and then you get your final, well, you get your time in seconds as 5.55 times 10 to the 3 seconds. Divide that by 60 to get it in minutes, because that's what it asked for, which is 92.6 minutes. So, and it takes an hour and a half for the International Space Station to go around Earth. That's pretty cool. Alright. Next, we have artificial satellites. These are the man-made ones that we launch up into space. Alright, so planets, moons, and comets are all natural satellites. They form naturally. We made artificial satellites, so they go and launch them into the Earth. Right, so we've chucked a grand total of 2,500 artificial satellites up there for the time being. They do a whole bunch of different things. So each satellite has to have a circular orbit that coincides with Earth's center. Orbits of artificial satellites must coincide with the center of the Earth, as the gravitational force applying the centrifugal acceleration acts along a line between the centers of the Earth and the satellite. So, with satellites, if they ask you to draw a satellite orbit, make sure that the orbit goes in between the middle of the planet. Okay? You can go at any different angle that you'd like it to, as long as it goes directly through the center of the planet, each way around. So this is the Earth. Has to go directly through the center, like all of these lines do. You cannot have an orbit that sits here or sits out here. If you launch a satellite that's out here, it cannot use the gravity, the center of the Earth, to remain in constant acceleration. It just falls into the Earth instead. Alright, next we're looking at a specific type of satellite called a geostationary satellite. So it orbits the equator in a period of 24 hours. Geostationary satellites orbit the equator at an altitude of approximately 35,900 kilometers, completing one orbit in the same time as it takes the Earth to rotate once on its axis. Okay, geostationary satellite orbits in the same direction as Earth's rotation, ensuring the satellite remains stationary over a fixed point on the equator. This property allows geostationary satellites to observe weather patterns over a specific area and transmit and receive communications from a fixed spot on the surface. The altitude of a geostationary satellite is calculated below. So, why do you think question for you? Why are geostationary satellites important? Why do you want a satellite to sit at one particular spot above the Earth and always remain in that one particular spot? What purpose would it have besides the one I listed? So, like I said in the paragraph, we often use it for weather, track movement of clouds, storms, high pressure systems, low pressure systems, all that kind of stuff, tracked by geostationary satellites because they stay in one spot and they follow the Earth as it rotates around. Okay, I'm not going to go through that entire derivative there. You guys can go through it in your own time. Okay, so moving on, we have a polar orbit satellite. That is a satellite that goes from pole to pole, just rotates around. North Pole, South Pole. Okay. So polar orbit satellite is an artificial satellite that orbits the poles of a planet at altitude ranging from 300 kilometers to 5,000 kilometers. Orbital period is much smaller than a geostationary satellite, allowing a polar orbit satellite to complete many revolutions each day. Orbital speed of a polar satellite at an altitude of 850 kilometers above the Earth's surface is calculated below. I'm not going to go through that. You guys can do it. They do tend to ask for satellite orbits in minutes, so make sure you remember to put your seconds into minutes. Make sure you do that calculation. Then we have medium Earth orbit satellites. Orbits above the equator at an altitude ranging from 2,000 kilometers to geostationary satellites at 3,500 kilometers. 35,900 kilometers above the Earth's surface. So between polar orbit and geostationary satellites. The most common applications of MEOs, which are medium Earth orbit satellites, are navigation, communication, and space environment science. For example, the Global Positioning System, or GPS, your GPS that you have in your phone, on your TomTom, if you're traveling in a car, is at a fleet of 30 MEOs, is a fleet of 30 MEOs at an altitude of 20,200 kilometers that provide location and time information to receiver anywhere on Earth. That is 30 satellites telling every single person on the planet where they want to go through GPS systems. That's nuts. Right? Then it has the orbital period of a GPS satellite is approximately 12 hours. They've calculated that on that page there. That is insane. Only 30 satellites for everyone on the planet. That's nuts. Alright. And then there's all the questions. Blah, 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 blah. And that's it for chapter 1.3. That's it. Done 1.3. Next week we can move on to relativity. Yay! Alright, bye.